Good morning, COP class. I hope you have been keeping physically fit as well as mentally fit. Let's continue with study theme 7. This is study theme 7, differential equations of heat transfer. Previously in study theme 5, we derived the control volume expression for the conservation of energy. In this study theme, we will add on to this previous knowledge and derive an equation for the general expression of the differential equation of heat transfer. We will also be introduced to the viscous dissipation, which we will then come back to in subsequent study themes later on. Special forms of the general differential equation of heat transfer are also introduced in the study theme, namely Fourier's second law of conduction, the Laplace equation in terms of temperature, the Poisson equation, and later we will also look at some common boundary conditions that we may apply to this set of equations for their simplification. Now remember, in order to formulate appropriate assumptions, we must be able to perform a proper analysis of the problems we will come across. We will also revisit steady state conduction as well as unsteady state conduction. And finally, we will look at convective heat transfer and specifically the concept of the fluid boundary layer. This concept will haunt future endeavors with regards to heat transfer, especially when we carry on with CIO, Chemical Engineering Design, next semester. Recall that the control volume expression takes on the following form, where we equate the heat, shaft work, and work to overcome viscous effects on the control surface on the left-hand side to the energy fluxes across the control surfaces, as well as the energy that is accumulated within the control volume. A control volume of infinitesimally small size will now be used to derive the differential form of the first law of energy conservation as shown here. For this task, we will consider an element with a volume of dimensions delta x, delta y, and delta z. First off, let's consider heat transfer, specifically the term del Q over delta T, and this equation is for heat transfer into the positions x, y, and z. Recall the heat flow in the x direction, shown here in the green, is perpendicular to the surface area made up by delta y by delta z. Similarly, heat transfer in the y direction, shown in red, and in the z direction, shown in blue, are perpendicular to the surface areas of delta x by delta z, as well as delta x by delta y. Now consider heat flow out of this element, specifically at positions x plus delta x, y plus delta y, and z plus delta z. We obtain the following relationship, and it is similar to the first equation. Next, let's subtract equation 2 from equation 1 and add an accumulation term as well. And in doing so, we obtain the following expression for heat flux through our control element. Note that the derivation in the textbook first deals with all other terms first before simplifying, but for simplicity, we will complete each simplification term by term. The overall simplification is performed by dividing the entire equation by the elemental volume of delta x, delta y, and delta z, and then taking the limit as the control volume approaches 0. Here, I only show this done for the first term and the accumulation term. So, after we've divided by the control volume, we end up with the following expression. After taking the limits for delta x, delta y, and delta z, we end up with an expression describing how heat crosses the control surfaces and accumulates within our control volume element. The shaft work term will not be taken into consideration for our purposes. The term specifically relates to work done within our control volume that for the differential case is not present. This is not the case for viscous work, as this adds heat to our fluid in question. We will substitute this term with the viscous work rate per volume, which is represented here by the Greek symbol lambda. After dividing the volume away and taking the limit as it approaches zero, we obtain the expression for viscous work. Realize that we would most often substitute this term with a numerical value, just like any other term. But generally, the effect of viscous forces on our fluid is small, and not much heat dissipates in this route. Next, we can simplify the heat transfer flux term, specifically at position x in the x direction, as well as at the position x plus delta x, also in the x direction, with respect to our control element. We divide this again by the volume and take the limit as it approaches zero. In doing so, the following expression is obtained. We can of course do this for all the other directions and obtain similar expressions in the y and in the z direction. This represents the heat, or specifically the energy flux, through our control surfaces. The last term that we will deal with is energy accumulation within the control volume. And this again simplifies to the following. If we divide by our volume and take the limit as the volume approaches zero. Right. Let's recap the derivation that we have just completed. So firstly, heat transfer through and within our control element is shown in the yellow. The viscous term is given by the blue term, and the energy fluxes through the control surfaces are shown in green, and the energy accumulation is given in red. This constitutes the most general differential equation for heat transfer, and we can apply analyses and assumptions to this equation for its simplification. Previously, we had a look at the substantial derivative, and in this case we can apply it to this equation in order to condense specifically the right-hand side as follows. We can also make use of the continuity equation and reduce the right-hand side further, as shown. Additional simplification can also be achieved if we use an equation that we will obtain later on in the Navier-Stokes section of the work. Note the viscosity term that is now present, given by the Greek symbol mu in the last term. If we are dealing with an incompressible flow, then the first term on the right-hand side of our equation becomes v dot nabla p. Notice that this first term on the right-hand side will cancel with the next term to the right of it, and the following equation is obtained. Next, we can also condense our equation by rewriting all of our heat transfer terms containing heat conduction, K, in the following manner. From these simplifications, we obtain the following equation. Realize that the terms representing the potential and internal energy may be expressed simply as the heat capacity multiplied by the substantial derivative with respect to temperature. The lambda term may be expressed as containing two portions. It's mainly made up of a normal as well as a shear stress term, shown here in the yellow. And for the case of incompressible flow, we can express the following equation for lambda. We realize that these two terms can then be combined into one term, specifically the viscous dissipation term. Now, with the simplifications complete, let us now consider special forms of the differential equation for commonly encountered situations. For the case of an incompressible fluid without any energy sources and with a constant thermal conductivity, we obtain the following expression. In the case where we have isobaric flow without any energy sources and with constant thermal conductivity, as before, we reduce the equation to the following. In situations where there is no fluid motion, all heat flow will be via conduction. If such situations exist, then we will typically be dealing with solids, and as such, the CV would be closely approximated to the CP for that material. Our energy equation then becomes as follows. Now, recall in the previous chapter that in some cases heat conduction was taken to be over a range such that the thermal conductivity remains constant, or we could treat it by some average value, and so it is more or less a constant. In this case, then we obtain the following equation by removing the thermal conductivity from the nublar sign. The ratio of thermal conductivity and ρCp is called thermal diffusivity. Compare its units with units for the other types of diffusivities you have encountered thus far. What do you notice about them? If we have a case, for example, where our conducting medium has no heat sources, then our equation will reduce to what is known as the Fourier field equation as shown. Occasionally, this equation is also referred to as Fourier's second law of heat conduction. For systems where heat sources are present, but there is no variation with time, we obtain the following expression, which we refer to as the Poisson equation. For systems where we have no fluid motion, so we have only heat conduction, we take the thermal conductivity to be constant. We also have no time variation or heat sources. Specifically, we are dealing with a case where we have steady state heat conduction with no heat sources. Then we derive the following equation, and that equation is referred to as the Laplace equation. So, in summary, the following is the generalized form of our equation. Remember that there were certain assumptions and analyses that we completed from the most general equation to get to this equation. What we do with the general equation is we analyze the problem statement very carefully, and in our analysis we will derive certain assumptions. Now, when dealing with problems, what I want to look for is that you complete an accurate or a reasonable analysis of the problem, and this will typically be reflected in your choice of assumptions that you've made. Using these assumptions on the equation, the general equation, we will derive a specific form of the equation. For example, here we have derived the Fourier field equation, where we have made the assumption that there's no fluid motion. We keep the thermal conductivity constant, and we also realize that there is no heat sources in our problem statement given to us. Remember that nublar is a condensed form of a more expanded form. So here specifically it's nublar squared, and so we are dealing with the second derivative in the x, y, and z directions with respect to temperature T. Now, if we only have a change in temperature in the x direction, this will be another part of our analysis. It will also reflect in our assumptions that we've made, and we will then derive a final equation that will apply to the specific problem in question. Now, let's talk about some commonly encountered boundary conditions. Let's start off with our initial conditions. We can have some starting constants, for example, given to us, where we say the temperature of a wall at time equals 0 is T0, and this is given by some constant value. We can also, for instance, be given something like a velocity, a linear velocity. We start off with 2.78 meter per second. These are known as initial conditions, and these conditions can change as the problem changes, or as we go further. For example, we could have a starting relationship. Let's say that temperature starts at some constant value at a boundary condition. And then as we move along the x direction, parallel to the heat flow direction, then we can have an expression. For every x, we add amount of 10 Kelvin to the initial condition of 294.5 Kelvin. We can also have the same for a velocity, etc. Now, we can also have boundary conditions, and this is what I have been referring to when we were discussing the initial conditions. Boundary conditions are conditions that don't typically change, whereas initial conditions could proceed to some final condition. Typically, you would deal with this in unsteady state heat transfer. So some boundary relationships could also be given to you, similar to initial conditions. The difference is that boundary conditions typically won't change. It just depends on what boundary you are analyzing. Is it a boundary inside a furnace? Is it the boundary outside the furnace, referring to the surface areas, for example? In summary, the following chapter dealt with the development of the differential equations of energy transfer, both general equations as well as simplified and special forms of these equations. We also went into some depth regarding boundary conditions and initial and final conditions. In the following chapters, we will be dealing with specifically steady state heat conduction that follows into an unsteady state heat conduction chapter. And finally, we will end off the section of COP with some more analysis regarding the convective heat transfer and the thermal boundary layer. Next up, we will do some examples for this particular study theme 7.